This is our conception of the house of stars in which we live. If you had spent your entire life locked up inside of one room in a house, you would have only the vaguest idea of what that house looked like from the outside. That is the way we are in our house of stars, which we call the Milky Way Galaxy. In this program, we're going to try to trace man's changing conception of the general dimensions and appearance of his house of stars as the windows in his little room out of which he was able to look became more and more clear. Now, if you look up in the sky in the summer and in the winter, you will see stretching across the sky a rather faint but very beautiful arc of misty light. You have to be at least 50 miles from the extraneous light of any big city, and this, of course, is the Milky Way. Now, we know what this is now, but man didn't always know. And some of the early conceptions, which we're going to try to tell you about, are quite interesting. The ancient Norse people, for example, said that the Milky Way was the road to Valhalla, and the few bright stars that stood out against the general background of this glowing cloud were the souls of the Vikings who had died honorably in battle as they mounted to this Norse heaven. The American Indians had a remarkably similar conception. They said that the Milky Way was the trail to the happy hunting grounds. But it was the more practical Greeks who gave us a rather down-to-earth idea of the Milky Way. They said that in the celestial stables at the top of the sky there was a cow. And one day this cow, as she was being milked, became restive, kicked over the milk bucket, and the milk ran down the sides of the sky. This was then the Milky Way. And the Greek word for it, the galaxy, is best translated as the Milky Way, and that's what we call it now, the galaxy. It was a puzzle to man. It was a luminous cloud which did not seem to change its shape under any circumstances, and it wasn't until about 1609 that we got an idea of exactly what it was, but not why. Then Galileo looked at it through one of his very crude telescopes. And crude as this telescope was, it succeeded in resolving this luminous cloud into countless stars, stars which were too far away for them to be seen individually, but whose light reached us from obviously a tremendous distance. There it was. The Milky Way was made up of stars. But why they were concentrated in this rather narrow lane in the skies, we did not know. Then, in the late 18th century, sometime in the 1780s, one of the great astronomers of all time, Sir William Herschel, was engaged in a tremendous survey of the skies. Herschel used a telescope which was large even by our standards, and one which he built himself. And in his survey, of course, he noticed what had been more or less apparent to everyone, that the distribution of the stars in the skies was not constant. Now, as Herschel started his exploration across the heavens, he found there were places where the stars were fairly thinly distributed. Then, as he went on, he came to places where the distribution was much closer, where the stars were literally packed into the space up there. This, of course, was the stream of the Milky Way. And as Herschel crossed it in his celestial journey, he came again to places where the stars were very thinly distributed. Now, in this survey, in this great star count, Herschel came across more than 5,000 little tiny cloud-like objects up there, which were obviously not single stars. Many of these, not many, say a few of these, had been known to mankind through earlier telescopes, and one or two even can be seen without telescopes. They looked like little clouds. and they were given the name nebula, which means a little cloud. Now, Herschel found a great many of them that were obviously clouds of gas with a few stars scattered in between them, no standard shape, any old shape, but cloudy. Then, as he began to pick up more and more of them through his more powerful telescopes, he ran into more and more which seemed to follow a pattern. Now, this pattern showed that these things were, they looked in some cases elliptical, in some cases they were circular in cross-section, and in some cases they were spindle-shaped. Now, here is one of the elliptical kinds. And you can see, if you look closely, that there are faint traces of what look like arms on the side of them. There are others whose arms are more definitely shown. We are looking at it perhaps more directly. And there are others, as I said, which have a sort of a spindle appearance, as though we were looking at them edge-on. There were a great many of these, and they all seem to form into this general pattern, seen at, in various angles. And to differentiate them from the true nebulae, the real clouds, which were obviously clouds, these were called spiral nebulae. And as discovery went on and as telescopes became better, they vastly outnumbered all of the other kinds. Now, there was one of these spiral nebulae in particular which was big and bright and obviously fairly close to the sun. And that we shall come to in a moment. But another result, and perhaps the most important result of Herschel's survey of the stars, was this. He came up with the first definite conception of this vast universe of stars in which we live. Herschel said that this is an irregular disk shaped like a vast wheel with an irregular edge, and that it is made up of millions and millions of stars, that it contains these little clouds of dust and gas, both the real nebulae and the spiral nebulae, and that our sun is a star rather close to the center of this great disk. This was the universe. It embraced everything, everything that man could see or could hope to see, according to Herschel, by whatever means that might come to his command. Now, among these spiral nebulae, which occupied a place in this wheel of stars, there was one which was very prominent. It was particularly bright and evidently fairly large and seemed to be quite near to the sun. And this is in the constellation of Andromeda, and was known as the Great Spiral Nebula in Andromeda. We can see it, of course, now, and it looks to us like an oval, an ellipse, rather. We know that its elliptical appearance comes from the fact that it is tilted away from us, that it is actually circular in cross-section. It seems to follow the pattern of so many of these spiral nebulae. Now, something like this, perhaps. Here is a model of a spiral nebula running true to form. You can see that it is circular in cross-section. But if we see it tilted at an angle, you see, it assumes an elliptical form. And it seems to have the definite arm structure that we can see in so many of these, which, according to Herschel, again, were included in our great overall universe. The Andromeda Spiral Nebula, of course, fascinated mankind because of its appearance, its mystery, and it has been one of the most studied objects in astronomy. The first historical record we have of the Andromeda Nebula is dated 925 A.D., when it appears, an account of its being seen. It can be seen without a telescope if you know just when and where to look. It's in the account written by Al-Sufi, a Persian astronomer. And from that time on, as man's methods of observation became better and better, the Andromeda Nebula was the one which was always concentrated upon. In 1916, the great telescope, then the biggest telescope of its kind, the 100-inch Hooker telescope at Mount Wilson in California, came into use. And Edwin Hubble, an American astronomer, pursued his studies of the Andromeda Nebula, which had been going on for some time, by means of this instrument. Hubble was able to resolve much of the Andromeda Nebula into stars, and the presence of stars had been suspected in what was generally considered to be a cloud of gas before that. Hubble noticed on many occasions that there would suddenly appear in that nebula a bright star. Now this was interesting but not very world-shaking, because such bright stars have appeared in many places in the sky. In fact, in the olden times, a star would suddenly appear where no star had been seen before, and men regarded them as new stars and called them new stars. And we still use the Latin name for new, the word nova, to describe such stars. Although now we know that they are not new stars. They are stars which have been there all the time, but which have been too faint to be seen easily. Then, due to some atomic imbalance which we do not fully understand, the star explodes. Sometimes blows itself to pieces, more often blows off thousands of miles of its outermost atmosphere, and becomes almost overnight 100,000 times as bright and hot as it was before, and is extremely easy to see. These are the classical novae. They stay bright for a little while and then fade back into insignificance again. In 1885, one occurred in the Andromeda Nebula, which became so bright that man could almost see it without a telescope as an individual star from the Earth. Hubble saw several of these novae in the Andromeda Galaxy, and then something happened. Hubble, in his studies of the nebula, saw that the same star became bright very shortly after it had been bright on a previous occasion. Now, there have been recurring novae, but they do not happen very close together. An interval of 50, 60 years, perhaps, separates those few that we know, which have twice undergone this celestial catastrophe. But Hubble's bright stars were coming back at intervals of a few weeks, and he knew that he had made a most important discovery. Here were variable stars in the nebula in Andromeda, and they were variable stars of a particularly valuable type. Stars that we call Cepheid variable stars, because of the prototype of this star was found in the constellation of Cephus. Now, a Cepheid variable is a giant red or yellow star, and its light varies in a regular cycle from bright through faint and back to bright again in a regular period of time that can be measured down to the fraction of a second. And the one valuable thing about this type of star is this, that the length of time it takes that star to go through its cycle of variation is directly related to the intrinsic brightness of the star, its real brightness. Now, if we know the real brightness of a star, we can, by comparing its real brightness with its brightness as we see it, its visual brightness, get a very excellent idea of that star's distance, for we know exactly how distance affects light, whether it be the light of a star or light of a candle. It affects light by what we call the law of inverse squares. Now, that means if we are twice as far away from an object which produces the light, that light looks only a quarter as bright to us, not a half as bright. So, when Hubble saw these Cepheid variable stars, these giant red and yellow stars in the Andromeda Galaxy, of the type with which he was very familiar, he knew that the Andromeda Galaxy lay at a certain specific distance, a distance which we had never been able to measure before. Now, here is a remarkable thing. In Herschel's early concept of this universe of ours, he said this universe is big, it's tremendous. It must be at least 100,000 light years in diameter. Now, a light year, remember, is not a measure of time, it's a measure of distance. It's the distance that light travels in a year at the rate of 186,000 miles a second. So that this universe of Herschel's was tremendous. But the Cepheid variables in the nebula in Andromeda told Hubble that the nebula in Andromeda was 750,000 light years away. And it must, therefore, be outside of Herschel's conception of the universe. And if that, as a typical spiral nebula, were outside, then all the other spiral nebulae might very well be outside. Here is our universe. Here is what Hubble found out about. that it was not the all-embracing disk of stars that Herschel pictured, that there was space outside of it, space which was populated by other disks of stars, other spiral galaxies. Now, see what's happening. We're getting a better look out of the windows of this room in the house in which we are. We are seeing other houses out there. And since we see other houses, all more or less of a pattern, it's only reasonable to believe that our house must conform to a certain extent to this pattern too. Now, if the Andromeda Galaxy is at a distance of 750,000 light years, we can then tell a great deal about its size. It covers a certain specific amount of the sky. And at that distance of 750,000 light years, the Andromeda Nebula, and we had better stop calling them nebulae now, they are galaxies as ours is a galaxy. The Andromeda Nebula probably forms one of this class of spiral nebulae or galaxies. Like this, has arm structure. We are seeing it tilted at a considerable angle so that it does look elliptical to us. But the arm structure is there, very definite. And as I said, at Hubble's distance from this, we have a pretty good idea of its size. Hubble said that at that distance, it must measure about 50,000 light years in diameter, say about half the size of our own galaxy, and have correspondingly about half the stellar population, 50 billion stars, as ours had 100 billion stars. And since all the other galaxies were outside, this led to a very interesting conclusion. We know that if we pass the light from any incandescent object, be it a star or a galaxy or anything else, through a spectroscope, an instrument built around a prism, there will be certain dark lines crossing the spectrum, that is the band of colors that is produced by that instrument. The position and the arrangement of these dark lines tell us a great many things about the object producing the light. And one of the things it tells us is this, that if these dark lines are shifted a little bit toward the red end of the spectrum from their normal position, it means that the object is moving away from us, or that we, the observer, and the object are moving apart. It works the same both ways. Now, here are several diagrams showing spectra of galaxies, and they shift toward the red end of certain definite lines. These are the lines. Now, see where they are in this first picture. They are a little bit toward your right, or toward the red. That means the position of these lines can tell us the velocity of that galaxy. In this case, it is 125 miles a second. And as we go out more and more distant galaxies, we find them moving more and more rapidly. Here is one in which the lines have been moved way up here, almost to the middle of this picture, which indicates a velocity of 14,300 miles a second. We did find that the nearer the galaxies were to us, the slower they were moving. The more distant they were, the faster they were moving. And the most distant galaxies, with which we were able to see and whose light we were able to see and analyze, moved at a speed sufficient to bring them to their positions in about 2 billion years. Now, here was a puzzle. Geologists know very definitely from various evidences that they can pick up on the Earth that the age of our Earth is between 4 and 5 billion years old, and yet the universe seemed to be only 2 billion years old. What happened? Was the Earth out there alone in space waiting for the universe to be built around it? That didn't seem to be conceivable at all. However, that's the way things were for quite a while. Now, as far as the appearance, general shape and size of our own galaxy is concerned, there were several other important clues which gradually came to light. And one of these clues deals with a tremendous formation of stars, the great globular clusters. Now, we know of about 90-odd of these clusters which are visible from our position here on the Earth. These are tremendous aggregations of stars. They measure about 30 light years in diameter and contain up to 100,000 stars. And they seem to be located on the very outskirts of our galaxy, of this wheel of stars, of our house, the stars in which we live. Now, Dr. Harlow Shapley, formerly of Harvard College Observatory, analyzed the positions and distribution of this group of clusters and said that they undoubtedly stood like sentinels around the edge of our galaxy. And this view of his was confirmed by our being able to see in other nearby galaxies that there were globular clusters situated on the outskirts of such galaxies, and we can see them here in their distribution. From their arrangement, Shapley said that the size of our galaxy was probably correct as we had known it, that it was a wheel of stars perhaps 100,000 light years in diameter, that it had a definite arm structure, and that it had a stellar population of about 100 billion stars, perhaps more, and of course various real nebulae, clouds of dust and gas within it. Shapley also said that we did not live in the center of this galaxy as Herschel had supposed, but that our position was off-center. When we look at the Milky Way in the summertime, it is extremely bright and very vivid, and Shapley said we are then looking in the direction of the nucleus, the center of this wheel of stars, the hub of it. And Shapley was able to give us a very definite idea. He said, here we have a diameter of the thing, 100,000 light years, this flat disk whose edge we are seeing. Here is the nucleus of it. Now, the nucleus is thick, perhaps 10,000 light years in depth from top to bottom. And from the varied appearance of the Milky Way as we see it, we can get an idea of our location in it. We live about 1/3 of the way in, from one edge toward the center, in one of the arms. When we see this summer Milky Way, we are looking from our position toward the center of that, which we cannot see because of the tremendous number of stars in it. In the wintertime, we are looking out toward the edge of this wheel, when the Milky Way is considerably less vivid. However, in the spring and in the fall, the appearance of the stars doesn't vary too much. Their scattering is just about the same, so that we probably live right about the center of the disk of the Milky Way, right in the central plane. This is what Shapley believed, that we were located about 1/3 of the way in, from one edge of our Milky Way toward the nucleus, say 30,000 light years from it, and just about in the center from top to bottom of the great system of the Milky Way. That is the way things stood until 1952, when an entirely new conception and new estimate came about. The agency responsible for this change was the great 200-inch Hale reflector at Mount Palomar, the biggest telescope in the world. Walter Body, an astronomer, took up a study of the Andromeda Galaxy with this telescope, hoping, at its distance of 750,000 light years, to be able to see a great deal of detail which hadn't hitherto been disclosed in that galaxy. Body was bitterly disappointed. The Hale telescope did not reveal what he had hoped. And he began to make a study of the clues which Hubble had used to estimate the distance of that. Now remember what Hubble had said. Hubble saw in the Andromeda Galaxy Cepheid variable stars, great red and yellow giant stars, with a regular cycle of variation. And this cycle led Hubble to believe that the distance of the Andromeda Galaxy was 750,000 light years. At that distance, its size, its diameter was 50,000 light years, and on that scale, the universe was perhaps 2 billion years old. Now, Body analyzed these stars and found the answer. These were not the red giant stars that Hubble had believed they were. They were, on the contrary, tremendously bright, hot blue stars, blue-white, at least 4 times as bright, perhaps more, than Hubble had thought they were. Now, that meant that if they were 4 times as bright, they were twice as far away, and that the distance of the Andromeda Galaxy, instead of 750,000 light years, was 2 million light years at least, that its size was about 3 times what we had supposed it to be, because it didn't look any smaller to us just because we knew it was farther away. It must be 150,000 light years in diameter and have a correspondingly larger stellar population, and that the universe on this new scale was about 5 billion years old. Now, you see, the Earth falls right into place. The Earth belongs. now and was not out there waiting for everything to happen long before the rest of the universe was built around it. To summarize the evidence we have, we live in a house of stars, and we have been able to see other houses which we believe are very much like ours outside. So, as I said before, we are justified, we think, in assuming that ours fits more or less into the general pattern. This house of stars is our Milky Way Galaxy, a vast disk of stars and dust and gas. This disk measures at least 100,000 light years in diameter. It has a stellar population of between 100 billion and 200 billion stars. It has an amount of dust and gas, and the dust and gas mainly concentrated in the outer regions of it, the arm structure. Our sun is just one of these billions of stars. And we, of course, are attached to our sun gravitationally. We go along with it. Our galaxy has a definite arm structure, and our sun is located, we believe, in one of the arms about 1/3 of the way in from one edge toward the center. The center, again, is the Milky Way, that part of the Milky Way which we see in the summer as we look toward the edge, toward the middle of this wheel, down one of its spokes, as it were, from our position about halfway between the top and bottom of it. In the wintertime, we see the Milky Way looking toward the edge, looking up the spoke, in the constellation of Taurus in the winter sky. The summer Milky Way, the hub of our galaxy, lies, we believe, in the direction of the summer constellation of Sagittarius. Now, this galaxy of ours is rotating in this direction, so that the arms trail back along the direction of rotation. And of course, like all celestial groups of things, its rotation is not like that of a wheel. It is rotating most rapidly in the center, and the different components are rotating more slowly as we go out. At our sun's distance, about 1/3 of the way in, our sun is traveling at a speed of about 175 miles a second. Yet at that speed, so vast is this galaxy of ours, that it takes about 200 million years for the sun to make one rotation, carrying with it, of course, its little family of planets, which include our Earth. This is our present conception of our house of stars in which we live. And to me, it is a tremendous tribute to man's ingenuity, to his thinking power, that he has gotten from his position as a prisoner inside of one room of this little house, this marvelous view of the great house of stars in which we live, our Milky Way Galaxy.
This is National Educational Television.